Hello and welcome to Extreme Gradient Boosting, XGBoost, in Python explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this particular video we are going to talk about extreme gradient boosting, which is a specific implementation and very efficient implementation of gradient boosting algorithm. And because it is a specific form of gradient boosting algorithm, and gradient boosting or boosting in general fall under ensemble learning. So we will start what are the different ensemble learning methods. Then we will see what is basically gradient boosting, and then we will see what improvements or what efficiencies are there incorporated in gradient boosting to make a full package called XGBoost or extreme gradient boosting. And finally we will see a practice of XGBoost in Python, and we will compare gradient boosting, naive gradient boosting algorithm with extreme gradient boosting algorithm. If you are new to AI Sciences, just to introduce AI Sciences briefly, at AI Sciences platform, we actually provide a lot of services regarding artificial intelligence and data science. The services include courses, consultancies, software, and much more. So in the description you can find the links so that you can navigate to different services that are available at AI Sciences platform. If you are new to our channel, you are welcome, and please subscribe our channel to get the latest videos and updates. And if you are a regular viewer of our channel, then welcome to another exciting video on the platform of AI Sciences. So let's begin. First of all, let's talk about ensemble methods. Ensembling is a very powerful technique of utilizing several algorithms or several models, not just one. There are a lot of different models on the same data, or sometimes on a different subsets of data that is trained. Several different models, they give you predictions. So think about model 1 as F1 on X, and that give its prediction Y. Then another, let me call this as Y1, the prediction. Then we may have another model that give a prediction Y2. So somehow we have to combine these predictions to utilize the power of both of these models rather than choosing just one of them. And there are several methods to combine the responses of different models. And these methods generally are categorized as bagging, boosting, and stacking. By the way, we have a full-fledged video on ensemble methods and separate videos on bagging, boosting, and stacking already on our YouTube channel. So here I will just describe these methods very briefly. If you want to see the details, we have full-fledged videos, separate and special videos for each of these topics and for ensemble learning in general. In bagging, what we do is we select different models. Sometimes all the models are same. How many models we are going to select is a hyperparameter, but we select a lot of models, different models. Maybe the model class, let's say all the models are decision trees, or all the models are support vector machines, maybe for supervised learning tasks, or we can select different models. For example, one SVM, one logistic regression, one decision tree, and so on. The key difference here is all these different models, let's say model 1, model 2, model 3, model 4, model 5, regardless of whether they are different or they belong to the same superclass of the models, like they may be all SVMs. In that case, they all belong to the same class. They can be all decision trees, they can be all logistic regressions, for example, or they can be different, like I explained earlier. But each of the model is typically trained on a different subset of data, and the outputs of all these or the responses of all these models to get the final response is normally averaged in the case of regression, and it is the maximum voting is usually performed in the case of classification. So all these models, they are completely independent, or at least in bagging, we need them to stay independent. One very famous algorithm that utilizes bagging is random forests. And by the way, we have a full-fledged video on random forest too, along with this implementation and so on. But that falls under bagging, and it's very, very powerful algorithm. In bagging, different models, they are trained in parallel and normally are independent, or at least we wish them to be independent for good accuracy. In boosting, the different models, they are built sequentially. So for example, you pick a model, whatever the model you pick, and you check its responses and see how this model has performed. Based on that, you pick another model. And based on the performance of first and two, you pick another model, let's say 3, and so on. So in that case, this boosting is more like sequential learning, and it utilizes the information of the previous models that have been chosen already. The boosting technique is more like sequential. The bagging technique is more like kind of parallel or independent. Stacking is also one very famous technique in which you select a model, maybe one or many models, and you, for example, you have 3 models, 1, 2, and 3, and you get the responses of these models, and now this response vector becomes another feature vector for the next layer, and you may have several layers. So let's say this is response y1, this is response y2, this is response y3, then this y1, y2, y3 becomes a feature vector. So different layers, they actually transforms your data to different feature vectors. The architecture is pictorially at least similar to neural networks. However, the learning setup or the training setup is completely different. In boosting, because today we are going to talk about XGBoost, so let's focus on boosting. By the way, we have separate videos. Again, I'm talking about separate videos that are available on our channel for bagging, boosting, and stacking, and Ensemble Learning in general. In boosting, the most famous algorithm is XGBoost, sometimes known as adaptive boosting. We have a full-fledged video on that already available on our channel. And there are other algorithms that fall in boosting, like gradient boosting. Luckily, we also have a full-fledged video, actually 2 videos in sequence on gradient boosting. And then an improved version of gradient boosting called XGBoost. So today we are going, and some other like light XGBoost or like GBoost, light GBoost. There are some variants other as well. We already have videos of XGBoost available on our channel, gradient boosting available on our channel. You can see the details of gradient boosting. There are two videos in sequence that explains bits and bytes and implementation of gradient boosting. Today we will just explain briefly what gradient boosting is, and then we will finally see how XGBoost is different from the naive gradient boosting. So in gradient boosting, what we really do is we pick different models in a sequence, and that sequence is generally adopted in a way that at the very first time you have to initialize your model. And normally this initialization, if this L, it refers to the loss function, and if you take, for example, the loss function being squared loss, if the loss function is being squared loss, then it can be shown that the initial prediction is just the average value of all the labels in the data set. For example, I varies from 1 to n, yi, and that is the initial prediction. That is the initial prediction for every data point. For example, it is the initial prediction for x1, it is the initial prediction for x2, and so on for xn. Now, these are our parameters. The parameters are really the predictions. The parameters are not the parameters of the model like W's in neural network or W's in SVM or so on. The parameters are really these predictions. Next, what we do is we compute the gradient of the loss of whatever the initial predictions are with respect to the predictions, and we compute the gradient values, sometimes known as residuals. Now, what gradient descent does is, whatever your model is, you take a step in the direction of gradient. So you can directly apply this gradient value here, or gradient vector here, and you can take the step. That's the naive gradient descent. But if you pick all the residuals and make another supervised learning problem and fit a model to learn the residuals or to smooth the residuals, that is one key difference of naive gradient descent and the gradient boosting. It actually fit a model on residuals or the gradients, and a specific residual or gradient is found by supplying on by finding out the response of the model. It can be shown that one-dimensional optimization problem can be solved. It's a convex optimization problem, can be solved depending upon the loss, of course. At least for the squared loss, this problem becomes finding out the learning rate becomes just very easy, and this turns out to be 1/2. For details, again, I refer the readers to our earlier video available on YouTube. We have all these details and derivations explained there. So you have your residuals or gradients, you fit a model, maybe a neural network or support vector machine, or maybe a decision tree, which is mostly the case. This model is a decision tree. That's a different supervised learning problem. And then you take a step in the direction of the gradient. But the gradient is not exactly applied found from here, but it's a response of another model in between model. And you do a lot of iterations, and you keep on updating your predictions. And finally, after all the iterations, whatever the maximum number of iterations you have set, your predictions will eventually theoretically and even in practically minimize the loss, and they converge to the actual targets. So that is gradient boosting. In our video, we also have explained stochastic gradient boosting, and we also have explained how to avoid overfitting using early stopping. So the readers are heavily or strongly encouraged to see or look at the videos to understand gradient boosting in detail. Now, this is the algorithm of gradient boosting. It does not focus on what kind of loss function you are going to come up with, whatever loss function the general framework worked with. What is the base learner, maybe a neural network or decision tree, or any decision tree, for example, card trees, regression trees, whatever model you come up with. The only constraint is this model, the base learning model, should not be a linear model. Otherwise, with squared loss and the linear model, for example, the whole framework will boil down to linear regression, simple linear regression. So it is good to choose this model, a nonlinear model. No matter what nonlinear model, you can pick that up. And then you just apply the step in the gradient direction, which is simply the gradient descent step. But we do not choose the gradient direction simply as a response of the derivative. Rather, we fit a model on the derivatives, and we pick the response from that model. And it turns out very, very famous algorithm, and very, effective algorithm in most of competitions on small to medium scale data sets. In XGBoost, for example, it's simply the gradient boosting algorithm, exactly the gradient boosting algorithm with certain differences. First of all, the main difference is in the model where you define the loss function, you apply a regularization. Regularization is in most of the cases is required and is recommended to avoid overfitting. Overfitting is a phenomena that your model is not performing well on unseen data, but it is performing very well on the training data. and that's a very that's a big monster in machine learning. And what really can be done is when you define an objective function, you can have a loss, for example this, sum over all I, and maybe plus lambda yi, or maybe yi square. So that might be one loss function. So the loss function incorporated with inside the model, incorporated with regularization term, that is one difference of the naive gradient boosting and XGBoost. However, we have explained in our earlier videos that we have posted on the our YouTube channel how to incorporate this regularization using early stopping without actually adding this regularization term. So although even if you do not add this regularizer term inside the model, you still can avoid overfitting using early stopping, a different technique in regularization. So I would say one difference of XGBoost and gradient boosting is simply the regularization inside the objective function, although you can have regularization in several other ways without actually incorporating inside the loss function. So that's one difference. Rest of the differences you will be seeing as most of the implementation details. I mean, making the implementation faster. For example, it utilizes a lot of cache. Cache is a fastest memory, you can say. Its access time is faster than RAM. So it's kind of implementation detail. It is made faster by using cache a lot. The other thing is that the base learners that they use in XGBoost are always decision trees. So they fix to decision trees, and the depth of the decision tree is pruned. The smaller the depth, the better or the most efficient or the more efficient the training process is. So that is also one difference. Although in gradient boosting in general, you can apply any base learner model, in XGBoost you are fixed to decision tree, and there is a pruning parameter inside. Next, parallel tree building. You can use this XGBoost in parallel environments, in clusters, in distributed environment, which makes it much faster than training a naive gradient boosting algorithm. However, we have explained in our gradient boosting videos earlier posted on our channel that there is a variant of gradient boosting called stochastic gradient boosting, or a further variant called mini batch gradient boosting. In mini batch gradient boosting, you can utilize a parallel distribution again on the naive version as well. Other differences are handling missing data. So XGBoost package has missing data handling inside and a built-in cross-validation capability. Although you can, even if you don't have built-in cross-validation capability, you can write it on top of that. Even if you don't have efficient handling of missing data, you can use some libraries to do that. But this XGBoost is really a package that actually has all these things available. I must say that although all these things are very fascinating, but one thing should be clear, that XGBoost, the difference between XGBoost, the practical difference between XGBoost and gradient boosting is simply the efficiency. That's the difference. I mean, if I compare these two, when I come to the package using XGBoost and gradient boosting, the main difference that I find is the efficiency. XGBoost is really fast as compared to the gradient boosting. In this particular case, in that case, this XGBoost, because it is implemented in a way that its training process is really fast, it actually becomes very much popular in most of the competitions. And not only the efficiency, sometimes it is much better than gradient boosting in accuracy, but accuracy is not the main parameter, I would say. The main parameter is efficiency. The way it is implemented, it is really fast. Let's see these differences also in the in some Python code. Let's just try out something in Python. So let's import this gradient boosting regressor. By the way, both gradient boosting and XGBoost, they come with classification as well as with regression. But the main difference between gradient boosting and adaptive boosting, AdaBoost, is the shift towards regression. They are best or basically very well suited for regression. Although the classification variants are also available, but they are, like, if you go for classification, I would say go for adaptive boosting. If you go for regression, I would say go for gradient boosting. But both gradient boosting and XGBoost, they both are also providing their classification libraries as well. So let's import gradient boosting and let's import this XGBoost. By the way, you have to install this XGBoost. Previously, it is not pre-installed. So you can just write pip install XGBoost and everything will be fine. You can play on some like data like Boston data. That's a regression data available, or you can make your own data by make regression. For evaluation, let's have a train and test split, and let's use the measure maximum absolute error. Yeah. So let's load the packages. And if you want to use the Boston data, you can have this command. If you are going to use your own data, you can have this command. If you see this train test split, if you see the total number of samples, they are 10,000. The dimension is 100. You can change the dimension. You can, for example, change the dimension to 50. And now this is the data set that is being generated there. That's a train test split. I will explain this code snippet later on when I will talk about efficiency. But let me move on to this code snippet in which the total number of base learners, I'm setting them to 500. And I'm also building a gradient boosting model and an XGBoost regressor. Both are regression models. And then I will see how much time the gradient boosting training algorithm takes and the XGBoost takes, because that's the main difference we'll be focusing on. Let's run it. It may take maybe a couple of minutes, so let's pause the video and I'll be back once this is done. Okay, so these are the times the gradient boosting algorithm took roughly 1 minute and 10 seconds, and the XGBoost took only 24 seconds. And this difference will become more and more as the size of the data increases or as the number of base learner increases. And here I have just written a code that actually will show if we change the base learners, if we just change the base learners. By the way, that's just one parameter. If we just change the base learners, you can see the difference between the training part of the training time of gradient boosting and the training time of XGBoost. And you will notice that as the number of learners will increase, the XGBoost become further faster and faster. Also, you should also try out as the number of samples and number of features they increase, the data set increase, XGBoost becomes faster and faster. And further, if you're running this on some cluster, some GPU machine or some cluster, some distributed environment, you will see a hell of a difference between the training of both. And that's the precise reason of choosing this XGBoost over gradient boosting in most of the time. As far as accuracy is concerned, I guess I should not talk about accuracy, because accuracy is kind of sometimes the gradient boosting wins, sometimes the this XGBoost win. But there are a lot of parameters to play with to gauge the accuracy very well. For example, if we see XGBoost regressor, if we just see that, and if we just see its documentation, for example, there are a lot of parameters to play with, number of estimators, the pruning depth, the depth of the base learners, the learning rate, and what should be the objective function, what should be the tree methods, and what should be the gamma in regularization. And there are a lot. I mean, whether you're going to apply regularization being L1 or L2, and I mean, there are a lot of parameters, and one can just play with these parameters and just set the parameters through cross-validation maybe to come up with very good accuracy. And maybe the accuracy, and in practice the accuracy can be made very well than gradient boosting by choosing right choice of parameters. But the efficiency is, I mean, is another story. XGBoost is extremely fast. So when we say extreme gradient boosting, I would personally say it's extremely fast gradient boosting. Yeah, so that's how I put this XGBoost in the picture. So that's about it. I guess you have enjoyed this video. If so, please press the like button, and if you have not subscribed our channel so far, just go and subscribe our channel, share our content with your friends and other people in this domain, and yeah, enjoy. We'll see you next time.